Like it,
computer
but
works.
take it as
Regular
a
or classical computers run on bits.
push up.
Bits can either be a 1 or a 0.
Let's take
Quantum computers, on the other hand, run on quantum bits, or qubits. Qubits can be either 1 or 0, or both, or a combination of the two at the same time. That's not wrong per se, but it only scratches the surface according to Scott Aronson, who teaches computer science and quantum computing at the University of Texas in Austin. We asked him to explain how quantum computing actually works.
Well, let me start with this. You never hear your weather forecaster say, well, there's a negative 30% chance of rain tomorrow, right? That would just be nonsense, right? The chance of something happening is always between 0% and 100%. Okay, but now quantum mechanics is based on numbers called amplitudes. Amplitudes can be positive or negative. In fact, they can even be complex numbers involving the square root of -1. So a qubit is a bit that has an amplitude for being 0 and another amplitude for being 1.
The goal for quantum computers is to make sure the amplitudes leading to wrong answers cancel each other out, and that scientists reading the output of the quantum computers are left with amplitudes leading to the right answer of whatever problem they're trying to solve. So, what does a quantum computer look like in the real world? The quantum computers developed by companies such as Google, IBM, and Rigetti were all made using a process called superconducting.
Okay, and this is where you have a chip the size of an ordinary computer chip, and you have little coils of wire in the chip, which are actually quite enormous by the standards of qubits. They're nearly big enough to see with the naked eye. Okay, but you can have two different quantum states of current that are flowing through these coils that correspond to a 0 or a 1. And of course, you can also have superpositions of the two. Now, the coil can interact with each other via something called Josephson junctions. Okay, so they're laid out in roughly a rectangular array, and the nearby ones can talk to each other and thereby generate these very complicated states, what we call entangled states, which is one of the essentials of quantum computing. And the way that the qubits interact with each other is fully programmable. Okay, so you can send electrical signals to the chip to say which qubit should interact with each other ones at which time. Now, in order for this to work, the whole chip is placed in a dilution refrigerator that's the size of a closet, roughly, and it cools it to about 1/100th of a degree above absolute zero. That's where you get the superconductivity that allows these bits to briefly behave as qubits.
-300 Celsius. Okay.
At IBM's research lab in Yorktown Heights, New York, the big tech company houses several quantum computers already hooked up to the cloud. Corporate clients such as Goldman Sachs and JP Morgan are part of IBM's Q network, where they can experiment with the quantum machines and their programming language. So far, it's a way for companies to get used to quantum computing rather than make money from it. Quantum computers need exponentially more qubits before they start doing anything useful. IBM recently unveiled a 53-qubit computer, the same size as Google's Sycamore processor.
We think we're actually going to need tens of thousands, hundreds of thousands of qubits to get to real business problems. So you can see we need quite a lot of advances, and doubling every year, or perhaps even a little faster, is what we need to get us there. That's why it's 10 years out at least.
Quantum computing would need to see some big advances between then and now, bigger advances than what occurred during the timeline of classical computing and Moore's Law.
Oh, we need better than Moore's Law. Moore's Law was doubling every 2 years. We're talking doubling every year, with occasionally some really big jumps.
So once quantum computers become useful, what can they do? Scientists first came up with the idea for quantum computers as a way to better simulate quantum mechanics. That's still the main purpose for them, and it also holds the most money-making potential.
So one example is the caffeine molecule. Now, if you're like me, you've probably ingested billions or trillions of caffeine molecules so far today. Now, if computers are really that good, right, really that powerful, and we have these tremendous supercomputers that are out there, we should be able to really take a molecule and represent it exactly in a computer. And this would be great for many fields: healthcare, pharmaceuticals, creating new materials, creating new flavorings, right? Anywhere where molecules are in play. So if we just start with this basic idea of caffeine, it turns out it's absolutely impossible to represent one simple little caffeine molecule in a classical computer, because the amount of information you would need to represent it, the number of zeros and ones you would need, is around 10 to the 48th. The number of atoms in the Earth are about 10 to 100 times that number. So in the worst case, one caffeine molecule could use 10% of all the atoms in the Earth, just for storage. That's never going to happen. However, if we have a quantum computer with 160 qubits, and this is a model of a 50-qubit machine behind me, you can kind of figure, well, if we make good progress, eventually we'll get up to 160 good qubits. It looks like we'll be able to do something with caffeine on a quantum computer, and it's never going to be possible on a classical computer.
Another potential use comes from Wall Street: complex risk analysis and economic forecasting. Quantum computing also has big potential for portfolio optimization. Perhaps the biggest business opportunity out of quantum computing in the short term is simply preparing for the widespread use of them. Companies and governments are already attempting to quantum-proof their most sensitive data and secrets. In 1994, a scientist at Bell Labs named Peter Shor came up with an algorithm that proved quantum computers could factor huge numbers much more quickly than their classical counterparts. That also means quantum computers, if powerful and efficient enough, could theoretically break RSA encryption. RSA is the type of encryption that underpins the entire internet. Quantum computers, the way they're built now, would need millions of qubits to crack RSA cryptography. But that milestone could be 20 or 30 years away, and governments and companies are beginning to get ready for it.
For a lot of people that doesn't matter. But for example, for health records, if health records could be opened up, that could compromise all kinds of things: government communications, banking records. Sometimes even banking records from decades ago contain important information we don't want exposed. So the problem we've got is we don't really know when quantum computers will be able to do this, or even if we'll ever build one big enough to do this. But what we do know is if you don't update your cryptography now, all the messages that you send over the next few years, the one you in history, could potentially be read. What this means is, for example, if you're a Cisco selling networking equipment, you're going to need to offer quantum-safe encryption as an option in the very near future. Because even though it doesn't look like we need it right away, if your product doesn't have it and the competitor does, guess which product gets bought?
What's next then?
One big issue facing quantum computing, other than increasing the number of qubits while keeping things stable, is that no one actually knows the best way to build a quantum computer yet. The quantum computers that Google and IBM and other companies show off are very much still experiments. There's also a big education gap. Not many people are studying quantum computing yet. China is pouring billions into quantum computing education, and the US Congress passed a law in 2018 called the National Quantum Initiative Act in order to help catch up.
Quantum computing capability via a rare commodity, which means that you want to invest in them now, you want to be hiring quantum computing knowledge, not necessarily to do quantum computing, because you want that intelligence to the organization so that you can take advantage when it shows up. Now, China has promised to put $10 billion in it, really upping its stakes in terms of the number of
That's also an exciting
PhDs that are going to start appearing.
aspect of what is China doing, Japan,
the world economy.
US and EU.
Other experts have compared Google's announcement to Sputnik,
What's the
the
price
Soviet
and
satellite
cost?
launched into orbit in 1957. The beach ball-sized satellite was the first man-made object to orbit the Earth. But Sputnik didn't really do anything useful, other than prove launching something into space was possible.
Many people are surprised that where exactly we are. For those who are just getting started, they like to make noise about vacuum tubes
Okay,
and Sputnik
this
and
thing
things like this.
looks very exciting indeed, and obviously they're working very proactively to keep it going with the design and engineering and fickling and all that, but there is just a small issue in my mind. How do they mass produce so-called quantum computers is that